This talk is about the phasor diagram of the brushless AC surface magnet motor. In particular, we will use the phasor diagram to explain the principle of flux weakening, which is so important in the high-speed operation of brushless PM motors. It's a personal view. Although it is generously hosted by JSOL, it does not represent JSOL in any way. This video may seem rather old-fashioned, even elementary, but the phasor diagram is an important visual tool that links the domains of the control engineer and the motor designer. I've used this chart many times before, and it helps to fix in our minds where we are in the family of electric machines. We're talking about the brushless AC permanent magnet motor. These motors are extremely common. They're used in electric and hybrid vehicle traction and in hundreds of tools and appliances where controlled motion and high efficiency are required. They're usually fed from current-regulated pulse-width modulated transistor inverters. Although we will concentrate on the surface magnet motor, the same principles also apply to the IPM, or interior permanent magnet motor. The surface magnet motor is simpler because its rotor is rotationally symmetrical. It has no saliency, and the synchronous reactances are the same in the D and Q axes. Because of this, it has no reluctance torque. The phasor diagram is practically the same for both types of motor, except in the values of the reactances and the resulting control laws for the D and Q axis components of the current. From a practical point of view, an important question in this talk is how to drive the motor speed up to high speeds when the EMF generated by the magnet exceeds the available supply voltage. Obviously, that voltage is determined by the voltage rating of the inverter. What is done is to use the inverter itself to drive a negative D-axis component of current, which opposes the magnet flux and reduces the net flux. We should really be talking about magnetomotive force, MMF, but the phase and magnitude of the current uniquely define the phase and magnitude of the MMF as a space vector. So the current is effectively a proxy for the MMF, and we can proceed further without complication. Pretty well everything in this talk is covered in the Green Book, Chapter 7, which is referenced at the end. This book is available in Japanese from MS Tech in Tokyo. Now, to start, let's construct the phasor diagram from scratch. The D-axis is laid out along the real axis of the complex plane, and the Q-axis along the imaginary axis. It's natural to associate the D-axis, or direct axis, with the open circuit flux of the magnet. In fact, the D-axis in electric machine theory has always been the main field axis, originally aligned with the axis of the field winding. This is the case not only in synchronous machines, but also in DC machines. In our case, the surface magnet brushless motor is a synchronous machine, so there's every reason to follow this principle. In a synchronous machine, we can express the EMF as J omega times the phasor of the flux linkage produced by the magnet on open circuit in each phase. Without showing all the details, the important point here is that J omega in the complex plane rotates the phasor by 90 degrees so that the EMF phasor lies along the Q-axis. We've labeled it OE here, while the mathematical symbol follows the Green Book boldface E subscript Q1. The boldface type denotes a complex number in time-honored tradition. The subscript Q is a reminder that the EMF phasor lies along the Q-axis, while the subscript 1 reminds us that the phasor represents the fundamental time harmonic component of the EMF waveform, which may, of course, contain other harmonics. Everything we do with the phasor diagram concerns only the fundamental time harmonic components of all the waveforms of current and voltage. All other time harmonics are left out. But to be completely rigorous, we should mention that space harmonics of the winding distribution do affect the values of the synchronous reactances. We don't need to study this in any detail here. The other important point about j omega is that the radian frequency omega is 2 pi times the fundamental frequency in hertz, and this is directly proportional to the speed of rotation. Therefore, the EMF is proportional to the speed of rotation. As the motor speeds up, the EMF is going to increase, and at some speed it will start to exceed the available voltage from the inverter. So here we've drawn a circle representing the available voltage from the inverter. We have given it the value 1 per unit, or 100%. We have also added the value of the EMF, which just happens to be 0.6657 per unit, or 66.57% at this speed. The available voltage from the inverter is the RMS AC value of the fundamental time harmonic volts per phase expressed in normalized form or per unit. The actual voltage waveform delivered by the inverter to the motor terminals is far from sinusoidal. The relationship between the AC fundamental voltage and the actual voltage waveform depends on the pulse width modulation strategy, as explained in the Green Book, Chapter 7. To find the motor terminal voltage, we have to complete the phasor diagram. First, we will add the current, this red phasor, OI. In the surface magnet motor at low speed, it is well known that the current is normally controlled to be in phase with the EMF, because this maximizes the torque. In fact, the torque is proportional to the product of the EMF and the Q-axis component of current, IQ. Here, the current phasor OI leads the EMF phasor OE by 11.09 degrees. Why 11.09 degrees? It's just an example, and it helps our discussion because we can see the components ID and IQ. The angle 11.09 degrees has the symbol gamma, and it is the angle by which the current leads the EMF. Some engineers use this angle beta, which is gamma plus 90 degrees. Beta is actually the true argument of the current phasor as a complex number. The component equations in terms of gamma are over here on the right. We can see that IQ equals 0.9808 per unit, which is very near 1, and ID is minus 0.1924 per unit. The per unit scale is convenient here, as it could refer to any number of amperes depending on the size of the motor and inverter. We can now complete the phasor diagram by adding the voltage drops in the armature or stator impedance. Starting at the tip of the EMF phasor at E, we first add the resistive voltage drop ER, or RA times I, in phase with the current. The magnitude is 0.2109 per unit in this example, and this is very large. We would see this only in a very small motor. In motors of a few kilowatt rating, the value would be of the order of 1/10 as large. but the large value here makes for a clear diagram where we can see the place of the resistance in the phasor diagram. Next, there is a reactive voltage drop, RV. In the surface magnet motor with no saliency, this is actually a plain reactive voltage drop, JXI, leading the current phasor by 90 degrees. Its value here is 0.6314 per unit. The sum OE plus ER plus RV is equal to the terminal voltage OV. It's as though the three voltages OE, ER, and RV were separate voltage sources in series inside the machine in each phase, and this is how we think of them. But later we should think about the use of the principle of superposition in this summation as to whether it is actually valid under saturated conditions. As it happens, the magnitude of the voltage OV is 1 per unit. This is not accidental. The base voltage for normalization has been deliberately chosen to give a terminal voltage of 1 per unit at this operating point. Why have we done that? Simply so that we can use this operating point as a basis for comparing other operating points, which is what we're going to do. We can see at the upper left that the phasor RV is resolved into two separate phasors, Rx and Xv. The first one is JXQ times JIQ, and the second one is JXD times ID. Since IQ is positive along the Q-axis, Rx is negative along the D-axis. And since ID is negative along the D-axis, XV is negative along the Q-axis. The components Rx and Xv are the dq-axis components of the voltage drop in the synchronous reactance. The effect is sometimes called armature reaction. Xd and Xq are equal, but in the IPM or any salient pole synchronous machine, they are in general unequal. With separate components, the diagram is set up ready to deal with the salient pole machine without any change in its form, only in the values of the reactances Xd and Xq. This form of the phasor diagram of the synchronous machine dates back to the celebrated French engineer André Blondel about 1895, and it has been used continuously since Blondel first published it. We may think that the dq-axis theory goes back only as far as Parkes transformation in 1929, but in fact it predates Parkes by about 30 years. I mention Blondel because in modern times we can calculate the d and q-axis components of flux linkage using finite element methods very accurately, even under highly saturated conditions. In that calculation we use Parkes transformation for the currents and flux linkages, but in textbooks and even in Parkes' original presentation, there is a very complex process in which the phase inductance matrix is diagonalized and, in ideal theory at least, relieved of its troublesome dependence on rotor position. The difficulty with this is that saturation makes a complete mess of the inductance matrix, regardless of the frame of reference. Blondel's so-called two-reaction theory sidesteps this mathematical can of worms, while still retaining the ability to deal with bulk saturation in the d and q axes. These ideas were not only known in the 1890s, but put into practice in design offices in more or less the same way that we do today. Moreover, the resolution of the reactive voltage drop into separate D and Q axis components helps with the control theory and with the dialogue between the motor designer and the control engineer. This is extremely important. Before we consider another operating point, let's take note of the power factor. That is the fundamental power factor. This is important because it's a measure of the electrical power relative to the volt-amperes provided by the inverter. So it tells us something about the required size of the inverter. The cost of the inverter is significant, and it's obviously related to its volt-ampere capacity. The power factor angle is the angle between OV and OI, and here it is 48.69 minus 11.09 equals 37.6 degrees. The fundamental power factor is the cosine of this angle, 0.792, and it is lagging because OI lags behind OV. Now, what we're going to do is to double the speed. We're going to do this while trying to keep the same current magnitude, 1 per unit. When the speed doubles, the EMF doubles and the reactances double. So the EMF OE goes from 0.6657 to 1.3314 per unit, bigger than the available voltage from the inverter. With the same current, the reactive voltage drop, JXI, grows from 0.6314 to 1.2628 per unit, while the resistive voltage drop, RAI, remains the same. The voltage drop part of the phasor diagram is drawn separately on the right, while on the left it is integrated with the main diagram. The main diagram shows that we must rotate the voltage drop part ERV about the point E so that the resulting terminal voltage OV returns to the voltage limit circle at 1 per unit. That is done by advancing the phase of the current from gamma equals 11.09 degrees to gamma equals 54.51 degrees, because the orientation of this triangle is determined by the gamma angle. We are assuming, of course, that the inverter can perform that phase advance. It's a current-regulated inverter, so it should be possible. But in simple terms, we should recognize that it can only do that if it has enough voltage available. If we tried to keep gamma equal to 11.09 degrees, the tip of the voltage drop phasor, EV, would be far outside the voltage limit circle, and we could expect a chaotic loss of control of the current waveform. It is in the magic of the control engineer that to get from case 1 to case 2 at 1 per unit speed to 2 per unit speed, this point V really needs to creep round the voltage limit circle without ever going outside it. So what we've ended up with is a rather nice example of the phasor diagram in a flux weakening condition. It's flux weakening because the d-axis flux that generates the EMF OE is opposed by the flux that generates the voltage drop XV. And this is entirely due to the negative or demagnetizing d-axis current ID. In fact, the resistive voltage drop and the voltage drop Rx don't help because they're tending to push the operating point away from the voltage limit circle. We can see that ID is much bigger than it was at the low speed, minus 0.8142 instead of minus 0.1924, so it's more than 4 times bigger. At the same time, since the magnitude of the current has remained constant at 1 per unit, the q-axis component, IQ, has decreased from 0.9808 to 0.5806 per unit. Since this is a non-salient pole motor, the torque has decreased in the ratio 0.5806 divided by 0.9808, which is 0.592. So we're going faster, but we've lost quite a bit of torque. The mechanical power, however, is the product of torque and speed, and it has changed from 1 times 0.9808 to 2 times 0.5806. So it has actually increased in the ratio 1.184. If we went any faster while trying to hold the current constant, IQ would fall faster and faster, and the torque would fall, and so would the mechanical power. The power factor angle at this high speed has actually improved. The angle between OV and OI is 10.3 degrees with a cosine of 0.9839, and that is the fundamental power factor, still lagging. The equations behind the phasor diagram are quite simple, and it's often possible to solve for the required angle gamma even with a closed form solution when the parameters are known. However, there is a point of profound importance to be made. The phasor diagram appears to rely on superposition. The voltage phasors or vectors are added together apparently without stopping to consider whether this is valid under saturated conditions. Under saturated conditions, the magnetic circuit is non-linear, and superposition cannot be expected to apply. The resolution of this question is interesting and I would say important. It depends on the way in which we approach the phasor diagram. If we start out with the assumption that xd and xq are constant and unaffected by saturation, we are likely to run into trouble, especially in a machine like the IPM or the wound field synchronous machine, in which the variation in these reactances can be very large. A common approach is to try to calculate saturated values of xd and xq. This approach runs into questions of uniqueness, as we will see. It might be interesting to note that in the classical theory of the wound field synchronous machine, which is quite a bit more complicated because of the variable field current, this is not even attempted, and alternative methods are used. A good way to look them up is an internet search for the Pottier triangle or Pottier diagram. Pottier was a Frenchman more or less contemporary with Blondel. Let's set this aside and suppose we measure the voltage and current and of course their phase angles, or suppose we calculate them accurately using the finite element method. In the figure, what we are calculating by the finite element method is the phasor RV. The phasor OR is simply resistance times the current phasor, so we don't need finite elements for this part. It must be possible to resolve the voltage phasor OV or the reactive voltage drop phasor RV into D and Q axis components, as for example we can see here. Vd equals minus 0.7512 per unit, and Vq is 0.6602 per unit. The purely reactive part of this voltage is Rv, which is V minus Ra times I. Rv is attributed solely to the fundamental time harmonic of the flux linkage per phase, and that is what we calculate using the finite element method. The problem now arises how to split or resolve this voltage, Rv, into the components OE, Rx, and Xv, which correspond respectively to the open circuit EMF EQ1, the reactive voltage JXQIQ, and the reactive voltage JXDID. In a nonlinear magnetic circuit, we just can't do it. Why not? Because the principle of superposition isn't valid. End of story. We might be able to extract XQIQ because it's the only phasor with a d-axis component, but in the q-axis it's impossible to separate EQ1 and JXDID uniquely unless we impose some other condition, for example assuming that EQ1 is constant even though it is not observable when current is flowing. We can see from this why it is not unreasonable to try to abandon inductance and reactance altogether and simply work with flux linkage, which is, I would say, the natural variable of a field solution, unlike inductance, which is a derived variable. Turning aside from these considerations, the question also arises, of course, as to whether there is a maximum speed. There will certainly be a maximum permissible mechanical speed determined by the physical strength of the rotating components and their bearings and dynamics, among other things. There will also be diminishing torque. Ultimately, the best that can be hoped for is to maintain constant power equal to the limit available from the inverter. What happens at high speed is rather a fascinating subject, and it is quite complicated. There's some discussion in the Green Book, Chapter 7, and of course much more in some of the references given there. Thank you for listening.